theta actually is a restoring force due to the elongation of the spring. Okay, so the elongation of the spring is equal to L times sine theta, because in this question, K1 is attached at the top of the radial bar, and this is the distance. Okay, vertical distance. Vertical distance is equal to L times cosine theta, and the moment resistance is equal to K2 times theta. So you don't need to calculate the distance, because the rotational spring provides the moment resistance directly. Okay, so from this equation, you can obtain the expansion about the applied force. Okay, and this equation is not important. Okay, actually you just need to linearize the equation. Linearized equation means sine theta is approximately equal to theta, and cosine theta is equal to 1. So if we linearize the first equation, we just need to linearize the first equation, we can obtain the equation about theta and p. And theta equal to 0 is a triple solution. And if you set the terms in the parentheses equal to 0, we can obtain the critical load. So this is a solution based on the equilibrium measure. Okay, we can also obtain the solution based on the energy measure. For the energy measure, we can obtain the strain energy due to the deformation of the two springs. So this is a translational spring. This is an elongation or deformation of the spring. So K times square of the deformation of 2 is energy from the translational spring. And for the rotational spring, okay, please understand, it is proportional to the square of the rotation. Okay, so here is a K times the rotation angle square over 2. And this is a standard formula to obtain the potential due to the applied force, so we don't need to talk in detail. And this is a total potential energy. After obtaining the expansion of our total potential energy, we can take a first derivative and the second derivative. Okay, so we obtain two equations, and then you just need to linearize these two equations, so we can obtain the linearized first derivative. Please understand, the first derivative must be a linear function about theta, so theta can be extracted from the equation, and then you set the coefficient coefficient inside the parentheses equal to 0, we can obtain the critical load. And this is the second derivative. If you substitute the critical load into this second derivative, you can have the conclusion like this. Okay, when p is less than the critical load, the second derivative larger than 0, so it is stable. Okay, and when p is larger than critical load, the second derivative is less than 0, so it is unstable. So this is a solution. Okay, so the solution when we have a single bar system. Okay, and for the second question, in the second question we have two segments, but please understand this is still single degree freedom system. So the most important thing is you are able to make a judgment how about the number of degree freedom. This is very important in your solution, even for the final examination question. Okay, so you have to understand how many independent variables should be defined, okay, to obtain all parameters. So this is a diffraction. In our case, we use the diffraction at the maximum location, at the maximum diffraction location as an independent variable. So this is a hinge. So rotation at the hinge location is allowed. So if we assume the delta, and then okay, for the left segment, the rotation angle is equal to delta over A rho, and for the right segment, the rotation is equal to delta over 1.5 A rho. Okay, so we can obtain the strain energy for the translational spring as well as two rotational springs. So for the translational spring, it is equal to K times delta square over 2. And for the two rotational springs, it is proportional to K times rotation angle square over 2. Okay, so we can obtain the strain energy, and this is a standard formula to obtain the potential due to the applied force. Okay, then we can apply the Taylor formula. So we have a 1 minus cosine alpha is equal to alpha square over 2, and 1 minus cosine beta is beta square over 2. Okay, so if you replace 1 minus cosine alpha and 1 minus cosine beta by Taylor formula, we can obtain the expansion about the potential due to the applied force. So this is the potential due to the applied force. And finally, we can obtain the total potential energy due for the system. Okay, usually it is a function. Each term in the expansion about the total potential energy is a function of the square of the diffraction or rotation. So when you take a first derivative, it must be linear function about delta. So delta can be extracted from the equation, and by set the coefficient terms before the delta equal to 0, we are able to obtain the critical load. Okay, and from the second derivative, we can obtain the stability behavior. Okay, so how about the stability behavior when the applied force less or larger than the critical load? Okay, so this is a final result about the critical load. Okay, so for the first two examples, it is easy to obtain the solution because both are single degree freedom system. So you just need to introduce one independent variable. It can be either rotation angle or diffraction. Okay, so and then we can obtain the total potential energy to get the solution. And now I show you the solution to example 3. This is a relatively difficult question. Okay, we consider a radial bar here. This is a radial bar, and for this cable, we can replace this cable by equivalent stiffness. Okay, equivalent stiffness, and the original inclined angle is equal to 60 degrees. Okay, and the applied force is not in the axial direction; it is in the vertical direction. Okay, so we want to obtain the critical load for this system, and in the solution, okay, because originally the cable is in the horizontal direction, so the restoring force is also in the horizontal direction. But after buckling, okay, there is a rotation angle for this cable, so the real spring force, the real restoring force should be in this inclined direction. But in this question, we only consider the horizontal, and we only consider the horizontal components. So you just need to calculate the horizontal elongation for this equivalent spring. Okay, and please understand here, theta is not the rotation angle due to the buckling. This theta means the angle after rotation. So this is an inclined angle, and so original angle is 60 degrees, and after small buckling rotation, the angle after buckling is equal to theta. So this theta is not is not close to 0. Please understand this point. Okay, this rotation angle is not close to 0 because this is not a rotation angle. Actually, it is close to 16 degrees. Okay, so we don't know the value about this rotation angle. Sorry, this is not rotation angle. This is an inclined angle after buckling. So this is a different point. In the previous question or in the example in the lecture, we always use theta to define the rotation angle due to buckling, and this rotation angle is very small, so we can linearize. We can use sine theta is equal to theta, cosine theta is equal to 1. But now, okay, because this is angle after rotation, so this is not close to 0. So you cannot use sine theta equal to theta, cosine theta equal to 1. Please understand this point. And now I show you how to obtain the work done by the strain energy due to the elongation of the spring. Okay, because we assume the energy is just due to the horizontal deformation. So you just need to obtain the horizontal components. The horizontal components means the distance. This is original rotation. This is rotation after buckling. So if we only consider the contribution in the horizontal direction, that means we only calculate the horizontal elongation. So horizontal elongation means a horizontal distance between this point and this point. So this is a horizontal distance, right? This is a horizontal distance. And this distance is equal to the distance from here to here minus the distance from here to here, okay? So the distance from here to here minus the distance from here to here. And the distance from here to here is equal to A rho times, cosine theta, okay? And the distance from here to here in the horizontal direction is equal to A rho times the original cosine 60 degree. So we can obtain the horizontal elongation. And how about the vertical displacement? Because now the potential due to the applied force is equal to negative of the work done by the applied force. Work done by the applied force is equal to P times the vertical displacement. And this vertical displacement is equal to the distance from here to here minus this horizontal minus the vertical distance from here to here, okay? And the distance from here to here is equal to A rho times sine 16 degree. And the distance from here to here is equal to A rho times sine theta. Okay, so in this way, we can obtain the solution. So this is a solution. And the horizontal extension is equal to, as I mentioned, is equal to A rho cosine theta minus A rho cosine 60 degree. Okay, and the vertical displacement is equal to A rho sine 6 degree minus A rho sine theta. Okay, so after obtaining these two displacement components, it's very easy to calculate the strain energy. Okay, so this is strain energy is equal to K times horizontal displacement square over 2. And this is a potential. Potential is equal to negative work done by the external force. So this is a P delta is obtained from here. Okay, so we can obtain the strain energy and the potential due to the applied force. Okay, and finally you can obtain the total potential energy. And then this is a don't worry about this delta. You just need to count the first derivative. So you can obtain the first derivative. This the terms in the parentheses is the first derivative. Okay, and the first derivative from the coefficient. Okay, for the first derivative, we can obtain the critical load. So you just need to set the coefficient before the delta equal to 0, so we can obtain the critical load. But the critical load now is a function about theta. Okay, but this theta, okay, is not the rotation angle. This theta is the inclined angle after rotation. So this theta is not close to 0. Okay, so how to obtain this theta value? If for any function, if you want to obtain the theta corresponding to the critical load, you just need to take a first derivative. Okay, but it is not so easy to obtain the solution about theta because this is a nonlinear function. So you just need to write down how to obtain the critical load. That's all. Okay, and from this equation you can obtain the solution about theta and substitute theta into this equation. We can obtain the critical load. Okay, critical load. So in this question, theta does not represent the rotation angle. So this theta is not close to 0. So this is a difference. Okay, it's a difference. And then we go to question 4. In this question, the degree of the number of degrees of freedom is equal to 2. Okay, and because we have two translational springs here and here, so I always recommend you to use the translational displacement as an independent variables. Okay, so we can have a y1, y2, or y1, y2. Okay, so here is the solution. I assume, okay, the horizontal displacement at the point B and the point C as two independent variables. So it's very easy to obtain the strain energy. You just need to use a standard formula to obtain the strain energy. And how to obtain the potential energy? We have 3 segments. Okay, we have 3 segments. For each segment, you assume the corresponding rotation angle. So when we have introduced a rotation angle, we use a standard formula. So for the first segment, second segment, and third segment. Okay, and after introduce rotation angles, you can transform 1 minus angle into angle square over 2 based on the Taylor formula. Okay, so please always use the Taylor formula. Okay, so 1 minus cosine theta is equal to theta square over 2. Please understand, this is not a linearization. Okay, this is not a linearization. This is a cosine function. Again, this is a cosine. This is a nonlinear function, and this is a nonlinear function again. So it is not a linearization because some students misunderstood. Okay, we just use the Taylor function to transfer the cosine function to polynomial function, but the polynomial function is still not linear function. It's still not linear function. Okay, so here is a rotation angle over 2. This is a nonlinear function, and then because we use y1 and y2 as an independent variable, so you have to represent the 3 rotation angle in terms y1 and y2. Okay, so we go back to for this member y1. Okay, so the rotation angle is equal to y1 over the distance from here to here. Okay, here is a y2. So for this member, the rotation angle is equal to y2 over distance from here to here. And for the internal segment, for this segment, the rotation is equal to y2 minus y1 over the distance from here to here, or y1 over minus y2 over the distance. It doesn't matter. You don't need to mind the difference between y1 and the y2 or y2 and the y1 because we always use a square of the rotation angle. Okay, we always use a square of the rotation angle, so you don't need to mind okay the direction about y1 because we only concern the square of y1. Again, here's the y2. So here actually phi1 is equal to y1 over 0, and phi2 is equal to y2 minus y1 over 0. and y3 is equal to y2 over L. So you can move out L square in the denominator from the parentheses. So we can obtain the equation about y1, y2. And then we can obtain the total potential. Please understand, because here we have two unknowns, so you have to take a first derivative about y1 and y2. Okay, and then you can obtain two equations about y1 and y2. But never, please never try to get the solution about y1 and y2, because now we are doing stability analysis, so y1 and y2 can be any value. So it is impossible to get a solution about y1 and y2. So please just set as a determinant. Okay, please just set as a determinant equal to 0. So that means this is a k11, this is a k12, k21, k22. Okay, so you just need to set the determinant. Okay, we can obtain the determinant equation. This is a determinant, and then we can obtain two solutions. You just need to pick up the smallest one. Okay, I want to mention, if you don't know how to calculate the determinant, okay, I want to mention 2 points. The first point is that, okay, please do not try to get a solution about y1, y2. Okay, this is a stability analysis. Okay, we just need to get a solution about A. Okay, rather than about y1 and y2. So please do not get solution. And the first approach is obtain the determinant. Okay, the matrix, the coefficient matrix. Okay, so this is a k11, this is a k12, k21, k22. Okay, and also if you don't know how to calculate the determinant of a matrix, I can recommend a different approach. So I'll show you the different approach. Okay, from the first equation or from the second equation, we're always able to represent y1 in terms of y2 or y2 in terms of y1, right? And then substitute, okay, this expansion into the second equation, so you can eliminate one unknown. So finally, we just have one equation about y1 or y2. Only each equation, the equation only involves one unknown, and then set the coefficient before this unknown equal to 0. That's all. Okay, so we can obtain the same solution. We can obtain the same solution. So it is not necessary, okay, to obtain the determinant of the coefficient matrix. So this is the reason I didn't show you the matrix. I didn't show you the determinant, because it is not necessary. Okay, and especially when the unknowns, the number of unknowns is larger than 2. For example, for 3 unknowns case, the matrix will be 3 by 3, so it is difficult to obtain the determinant. So in that case, you at least to reduce the number of unknowns or the dimension of the equation by 1, at least reduced by 1. So makes the determinant is corresponding to a matrix 2 by 2. Actually, you can reduce 2 from 3. So finally, just one linear function about one unknown, and then set the coefficient before this unknown equal to 0. You are already able to get the solution. So please try to use this way to get the solution. Actually, this is a question from past paper, from the examination paper last year. Okay, so maybe this year I put a similar question again in the final examination. I hope you can understand how to get a solution for a question like this. Okay, for a question like this. So when we have two unknowns, I always recommend you to use translational displacement as an independent variable, but you can also use rotation angles. Sometimes maybe rotation angles are convenient to get the solution. Okay, so it depends on the time. It depends on the question, because in this question, the springs are translational spring. So definitely y1 and y2 are appropriate. But when the spring are rotational spring, maybe the rotation angles are more convenient to get this solution, especially for the total potential energy. For the total potential energy, for the strain energy, when the springs are rotational spring, of course, you assume the two rotation angle at the spring rotation, the energy is just equal to spring stiffness times rotation angle square over 2. So it is easy, it is direct, to obtain the solution. So this is a solution for tutorial 1. And then we go to the lecture